Okay, so going back to the example that we started with, for graph isomorphism, we've got those exact same graphs G1 and G2. We've already basically identified that these are isomorphic to each other. But let's prove it. Now, the definition of isomorphism says that there exists a bijection between the vertex sets that preserves adjacency. So to prove that these are isomorphic, we need to identify what that bijection is. Now, there's more than one. There could be more than one right answer. Almost always, there's more than one way of doing this. But we need to find one. So I'm gonna build a bijection over here between the vertex sets. And I'm going to go ahead and do it by writing out the vertex sets in columns. It's up slightly. A, B, C, D. There we go. And V2, X, Y, Z, W. And then I'm going to define my bijection or my function with just arrows. So what I want is I want to have A and C, which are the tips of these two triangles that are sort of sticking up, like going, sharing an edge over here. A and C have to be identified with the tips of the two triangles here. Now here, it's as if this piece of paper was folded along this line. It's like a paper was folded right along this line here. And now we're viewing it from the side where it's folded in half. And this is that edge where the fold occurred. So the two corners are the W and Z vertices. So I want to associate A and C to W and Z. It doesn't really matter what order I do it in. So I'm going to have A map to Z. Oops. And I'm going to have C map to W. I don't know why this is not working. C map to W. I think I have a notion of why it's not working. See if I can fix it. There we go. So A and C map to Z and W. Good. Now I need the other vertices D and B to map to X and Y. And again, the order doesn't really matter in this example because if I swap D and B, then I get exactly the same graph I started with. There's some symmetry to the original graph G1 itself. So I'm just going to have B map to X and D is going to map to Y. Okay, so there's my function defined. This is clearly a bijection. I don't really need to prove that it's a bijection if you can look at it and tell that it is both one-to-one and onto. Right, clearly based on those arrows, it's a bijection. Okay, establish the bijection. But now I also need to prove or show that this F preserves adjacency. Now, to do that, to show that F preserves adjacency, what we're going to do is make adjacency matrices for G1 and G2 for both graphs, and we're going to order the rows and columns in a way according to our bijection we made. So what I mean by that is if I make the graph or the matrix for G1, if I make that with my rows and columns in alphabetical order, A, B, C, D, A, B, C, D, then what I need to do for G2 is make sure that the rows and columns are ordered so that they correspond to the order of the A, B, C, D. So since A maps to Z, I have to have my first row and first column be Z, right? So that it corresponds to A. What I want to do is I want to set it up so that the entries are going to line up exactly with each other. Now B maps to X, so X is next. C maps to W, so, and then D to Y. All right, So there we go. So now I have arranged my rows and columns so that according to the bijection I've defined, so that they are lining up with each other. Now I'm going to make the adjacency matrices. I'm going to pause the video and write all those entries in. You can do the same. Can I pause the video? All right, there we go. So I have made the adjacency matrices for G1 and G2, and we see that they are equal to each other. So we can wrap up our proof with a short couple of sentences at the end. We can say, since the adjacency matrices for G1 and G2 are equal, F preserves adjacency. So that means F is a it's a bijection. It preserves adjacency, so it is an isomorphism, and therefore G1 is isomorphic to G2. Awesome. All right, so looking back over this, this is an example of proving that two, gosh, what did I do? There we go. This was an example of proving that two graphs are isomorphic to each other, right? We first identify what is the bijection, or what is a bijection that we could make, and then we show that that bijection is going to preserve adjacency by making these. Now, this step is essential. You can't skip this step, and the reason you can't skip this is because there's a ton of different possible bijections you could make that don't preserve adjacency. As long as you have the same number of vertices in both graphs, then you can make a bijection between them. But that's no big deal, right? That doesn't really tell you anything. You know, you could have one graph with 10 edges and another graph with only 3 edges. Obviously, they're not isomorphic, but you can make a bijection between the vertices. So the meat of it is showing that the bijection you made does preserve the adjacency by showing that when you reorder the vertices according to that bijection, you cause the adjacency matrices to be equal. Okay. So that's it for now.